we really want to include a lot of practical things to this. Not much theory, but a lot of practical terms. So we hope very much that you can enjoy it and you can take profit, the newcomers as well as the experts. Now, today, we really focus from samples to first results with IGC. So we are talking about a lot of different samples, how to prepare them, how to fill them in, and really a lot about the experimental conditions. And results, not so much today, but you'll find this in the other presentations. Before we dive into this, I would like to have a short outlook of what we usually experience, what your problems are. So why is IGC being used? And a very short explanation about the physical principle of IGC for those who are really new and have heard about this to get an understanding from our point of view. So, getting to your questions, what we usually experience is, with our clients is that they have issues like our products are somehow within specification, but somehow they behave differently. Why? How can this be explained? Or surfaces are being modified and it needs to be some know-how what makes the differences. Different treatments or batch-to-batch variations which have very little explanation, despite that they behave differently. Stability issues, especially in pharma, also amorphous phases. Sometimes, yes, we deal also with academic questions, but mostly we deal with industrial questions who really require this kind of analysis. You see also a type of products we are analyzing, from fillers, mineral oxides, pigments, battery materials, catalysts, APIs, excipients, polymer films. So this is really wide. But there's one common theme here. There's a need for highly sensitive and quantitative and reproducible characterization methods of surface interaction properties. And this is beyond, of course, we know all the different analysis like specific surface area, the images you have, the chemical analysis, for example, by XPS or by FTR, and a lot of different applications. But so far, we concentrate on the surface interaction potential. Now, very briefly, what does IGC or inverse gas chromatography consist of? The basic principle is that we're using different gas probes of different kind of properties to touch the surface. There are different concentration ranges, very small concentrations, which we focus mostly today, but also very high concentration, we really cover surface. This has been covered by our first webinar. But now about the gas probes which we're using. Usually we have a set of 15 different gas probes, but I will show only 4 as some examples. So starting with the N-octane here. So we have a class of linear alkanes, and the principle is always the same. They touch the surface, they absorb them in an inert gas stream, and the stronger they touch, the stronger the interaction is. That's a basic principle. And we take these probes as probes for the surface properties. So the N-octanes are apolar. They provide the dispersed surface energy. We are also using more bulkier molecules, like here we have isooctane. This gives some knowledge about the nano roughness, where it can come in, or cyclooctane about some solubility. But I've also, as an example, shown 2 extreme polar probes. One is chloroform, which is an electron pair acceptor, as Lewis acid, so it touches on the Lewis base centers of the surfaces. And de-ethyl ether is the other one. Is an electron pair donor, a strong electron pair donor. So here we touch the acidic sides of the surfaces. So the principle is hopefully clear. As I said, we don't dive into this theory much more. The question is, we need to have quantitative properties, and the key properties we have, we call them dispersed surface energy, nano roughness, polarity, or acid base values. Now, practical setup for those who don't know this yet. We have an instrument. This consists of GC. We have gas probes. We can inject headspace or liquid injection. So it's a huge variety from concentrations, even very, very small concentrations. And this instrument, the overall instrument setup was developed by Adcentis and is available under our brand name Neuronic. The samples, and we come to this in much more detail, are filled in usually in a column. Inert gas is flown over it, and in this flowing inert gas, small quantities of these probe molecules are being injected and then interaction with these unknown solid surfaces. Here is the retention time, and you see this little red peak. This is methane as an indicator, as an inert indicator, but which is detectable. And you see here the retention time of the probe. And the time here is a measure for how strongly this absorbs to the unknown surface properties. Of course, there's a lot of data treatment and so on behind this. That's a lot of experience we have, so we don't bother about this today. Very short note about ourselves. Adcentis was founded 21 years now, in year 2000. There are regular 70 clients, mainly industry, all over. There are over 800 different projects, a lot of different pages of reports. And I myself, I'm a key partner of Adcentis since 2014. I work very closely together with Eric Brentle, which again, I apologize, he cannot be here. And we started to develop our own instrument in 2017. But we enjoy also a very active community here. We started a round-robin test with 12 different organizations. It's been increasing. And for those who are participate and those who are joining in this webinar, yes, very shortly we will inform you about the next step. We also have a regular annual IGC symposium, and we are happy to have this here. Also, you see Professor Stephen Abbott, he's joining here. Hello, Stephen, nice to see you. And he wrote a book about IGC science, which is free, available on his web page, and we really like to collaborate with him as well. Now, let's dive into the really interesting topics, examples of our samples. Here, I've made a few pictures, for example, cement, pigments, and so on. But it's not only powder, it's also fibers. And I've shown a picture of glass fibers. And no, this is not carbon fiber, but we do also carbon fiber. It's hair. In this case, it's Chinese hair. And the question was, how does a treatment here changes the properties of the hair? Of course, that's part of the cosmetic industry. We can also study surfaces of coated steel plates, so meaning of plates, but there's also be of polymer films in this sense. And yes, we can do this also. Any products which have a very low vapor pressure, as oils and polymers, we can study with the same methodology and then calculate the HSP values, for example, using the HSP IP software provided by Stephen Abbott. Different types of columns. You see here the stainless steel column. Of course, that's chromatographic grade, so really very well purified inside for powders and fibers. But you see here also the one, it's not really a column, it's more a plate, but you see here the gas channels underneath the plate to be studied, and this interaction can also well be measured. So we're having two devices. Mostly we use the tube, yes, but for special studies, we use a device for the flat surfaces. Now, column preparation. So that's why what I'm focusing here is, you see here some materials which we're using, like the glass wool, the column, the pin set, also the sample, the funnel. And I would like to show a few videos here. Yes, and so that's how we prepare the column. You see, we can have different lengths, relatively easy in this case. Prepare the column, prepare the tube for this, for the filling. So that's how we do this. And on the other hand, that's the filling. So we use the glass wool to stop the samples going into the gas flow. But you see also how the glass wool is being stuffed here to provide a good surface for the powder surfaces. Now, the sample is not in the column yet, but that's something we will show here. So the column is closed as such and being weighed. So don't forget to weigh the column before you fill in the sample. That would be really bad. Now I want to show you how we fill the column. And so that doesn't look so high sophisticated, but there are these little tricks to this. And you will hear this very soon, what this little trick means. Yes, I hope it's not too loud. But by this vibration, it's a very well packed column. And again, weighing afterwards to really make sure that we know exactly the amount of sample in this column. So we have some more complex cases. What, for example, if the powder is very fine and you suspect that there might be a blockage of the gas flow or very high pressure drop, or you experience this and have to counteract on this one, we have a good practice, and that is sieving. So if you have some materials which is around, let's say, over 100 micrometer, that gives a good fraction of this one. But if you have very, very small powder, let's say even in the below micrometer range or in the nanometer range, you can slightly compact this and then sieve it afterwards. So the particles itself, and you see this here, they look like a raspberry if you magnify them, and the gas can really go very well in. There's no diffusion limitation in this range of particle size. We check this, of course. So that's really a good method to improve the pressure drop and the overall gas flow. You will see later on how this works. So this is a non-compacted and non-sieved powder, and this is the slightly compacted and sieved powder. You see that it has a totally different granulometry, and we can use this. So now mounting the columns in the oven, you see a gas chromatograph. That's the one we use. It's really nice. It has a very homogeneous, very stable temperature profile. And not only this, you can pack also a lot of different things in it. If you have a GC with 2 injector ports and detectors, we can run 2 columns for parallel measurements, and that's also what the automated system, what we have, is providing. So that's this setup. Before we start, one thing about column conditioning. The objective here is really to stabilize the surface in the inert gas stream and increase thereby also the reproducibility. There are 2 different variables here, temperature and duration. Usually we say in minimum 2 hours, but better overnight. We found there is not so much different. We have slightly better reproducibility if we have it overnight, but let's say 2 hours is usually also okay. The temperature, we try to condition at slightly higher temperatures than we do the measurement to be on the safe side, but sometimes that's not possible due to the sample properties. Now we are ready to start. I have thought about how to describe the lab protocol and the experimental conditions, because you have a lot of different variables which you can turn and change. Let's say the key variables so far are the sample quantity in gram. Of course, this provides a square meter, the overall total square meter, which is in the column. We have the gas probes. We have the temperature. Temperature is very important. We have the injected concentration of your gas probe. And we have the column diameter and length. And also the gas flow rate. Yes, we have also the sample property, which I've shown here in black, but sample property is not really a key variable. It's something you have to take. And this is really the unknown in this whole kind of equation. There are certain key observables to define the lab protocol. One is the retention time, one is the peak shape, and also the pressure drop, which I mentioned before. There are certain constraints in really practical measurements. Yes, the net retention time of your gas probe should be something observable. So we say, okay, at least maybe 10 seconds longer than your methane peak, or better 20 seconds. But there's also maximum. Sometimes the absorption is very strong and you have to wait and wait, can up to 60 minutes or 200 minutes, but 200 minutes is really the maximum we are usually employing. It must also be a detectable signal. Then we ask the question, how symmetric is the peak, pressure drop, and some samples like pharma products are very sensitive to temperature as well. So there might be a maximum temperature here. What I'm doing now with you is first give an example about the net retention time. Here I have two chromatograms, and the first peak is the methane peak. The second peak is the pentane peak, because we usually start with the short N-alkanes, like pentane. And you see this here, the resolution is not good enough. So you have to increase either the sample quantity or other factors, which I will discuss. But this one here would be really okay. Now, I have three, let's say, three views which I would like to explain this overall scheme to get to your lab protocol. The first one is the quantity of your sample in the column, the temperature and the retention time. So how do they correlate to each other? In practice, we can employ 50 milligram to 3 gram. So that's a practical range. And the temperature between 25 degrees and up to 200 degrees. We could also go higher, but that's very, very rarely required. Now, the key observables are the retention time here in this sense. We have a certain degree of freedom with respect to the gas probes, because we can change the different N-alkanes from C5, pentane is quite practical, to C10, decane, or maybe even dodecane. We also employ, as I mentioned in the beginning, cyclic and branched molecules. Here we usually have the C8 series, so cyclo and isooctane, but if the retention times are too long, then we can employ also shorter cyclo and isoalkanes, as mentioned here. Let's take an example here. So this has been silica, analyzed by 110 degrees, different samples. And this is a carbon number, meaning the number of carbons in the N-alkanes. And this is a free absorption of free energy of absorption. And you see here, this kind of samples, we employed decane. For all of them, we had series of heptane, octane, nonane. But those with a stronger interaction required then the shorter N-alkane, which is possible. And this was hexane in this case. So this works relatively well. So you can play a little bit around with this one. Now, problems are often polar probes, especially on oxides as silica. I've written here all polar probes which we usually try to employ. And when we start this kind of experiments, we have two things to consider. The first one is the ethyl ether. Is it too long? That can happen relatively easy on oxides, yes. Or with chloroform, is it too short? So if it's too long, we can increase the temperature until it's in a reasonable range, but beware that the chloroform might become too short. So this is a kind of trade-off which we have to find a reasonable way of working within these constraints. There are certain substances or certain samples where even all this kind of optimization fails. And in this case, we have a kind of last resort. We're using two columns, a short column for the polar probes and a long columns for the non-polar probes, and combine the data. So that's also possible. But it's more effort, so we try to avoid it. But if possible, that's also okay. Now, the second, let's say, point of view is about the injected concentration, the peak shape, and the detectable signal and the peak symmetry. Let me explain this. The requirement for inverse gas chromatography from the theory is infinite dilution. That means there's no interaction between molecular probes on the surface and on each other. So this is a very defined kind of condition in IGC as such. Here is an example of different N-octane concentrations over silica. And you see here the different quantities of vapor injection we use, from 1 microliter to 25 microliter. These are the smallest injection volumes, and these are the larger injection volumes. And what you see is that already at 8 microliter here, that's marked with a blue arrow, there is a kind of change in the retention time. And that's something you really should not want. This really 8 microliter, we calculated this, and this corresponds to a monolayer area of N-octane of 0.018 square meter, which is very small, because sometimes you have 1 gram of silica, might be 100 square meter. You're really talking about low percentages of probe in this column. Yes, I know there is also the term surface coverage here. We try to avoid it. It's a nominal surface coverage. It's an average over the whole column, and you see the peak is traveling through. So the surface coverage in the peak is quite little defined, and we try to avoid this. So for us, infinite dilution is the key to achieve, and it can be done. It can be done, but it needs a sensitive detector and the cautions I mentioned. Now, another remark about the injected concentration and the peak shape. I mentioned before that polar probes are sometimes difficult. And with this example, I'd like to show also what happens sometimes if you have acetone, a polar probe, at different high concentrations. And here you see a chromatogram. Here's the time, retention time. Here's the signal intensity. And these are different quantities of injected acetone. I kindly got this figure also from the group of Professor Völker from University of Poznan. Thank you very much on this one. What you see here is that the observed retention time or net retention time varies quite a lot by the concentration. Some try to interpret this in terms of nominal surface coverage or surface coverage. We at Centis and Inolytix try to find this, the lowest concentration, infinite dilution, and work on this one to be very defined on this. So, conclusion here, polar probes are sometimes not easy, but small concentrations help. And if you're really looking for a specific polar probe and really want to cover the surface in a defined way, there's also the way of IGC finite concentration, means a surface saturation under defined conditions, and that provides the isotherm and also heterogeneity measure of the surface as such. If you're interested here, you can look this up in the first webinar on YouTube. Now, coming to the third aspect, the dead volume, minimal quantities, and something called theoretical plates. I have shown practice 50 milligram to 3 grams. Practice also is that we have columns of 2 to 4 millimeter inner diameter, and lengths between 5 to 20 centimeter, can also be longer if really desired, and flow rates of 10 to 20 milliliter per minute, depending on the inner diameter. Why is this? There are certain sources of peak asymmetries. First, dead volume. Dead volume, you have dead volume if you have only a small sample size, but a long column. This is just that volume, which doesn't really help to make a nice peak shape. It can also be unfavorable or bad column filling. You have seen how much care we took to fill the column. So this is very reproducible. If it's done differently, you don't really know what happens here. There can also be channeling, and that happens with very fine powder. And if the pressure drop is too high, then the gas flow finds a preferred way through the bed, and that is not the best way, of course. So therefore, this slight compacting and sieving is really a good way to avoid also this. High concentration of gas both, we have already touched on this one. Low measurement temperature, yes, if you have a low measurement temperature, maybe also close to the vapor pressure of the probe, then the desorption and adsorption processes are not as homogeneous as we would like to have this for a good RGC signal. Now we come to the low number of theoretical plates. I have an example here, but first, yes, there are strong interacting surfaces where there are just asymmetric peep. We cannot help this one, so that also happens. But now to something called like number of theoretical plates. If you look this up on the internet, you find a lot of theory, Van Deemter curve, and so on. I will like to make this short, and I have an example here with something with a higher quantity, 144 milligram of sample in the column, and something with a smaller quantity of 56 milligram in the column. And you see a difference here. And that means the higher quantity is a longer column that absorbs better. So here you have a much better chance of adsorption, reabsorption, and so on. It averages out much better. That's also the reason why you need long columns in GC separation. You just have a better separation on this one. If you try to minimize the retention time, for example, with polar probes, if it's too long and take less and less, yes, you're also causing a problem for asymmetric peaks because the separation performance in your column is not good enough. So I hope this example was illustrative enough for you to consider also this aspect for peak asymmetry. Now, I assume now that you have found your sweet spot, your lab protocol. Everything is fine, the measurements being done, the constraints are being considered. Now you can have the results with high reproducibility, it's being quantitative, and you have the conditions you need with your task. You can get values like dispersed surface energy, the polarity, acid-base constant, nano-roughness, and we really like nano-roughness in our case because we can very reproducible define some solubility, important, for example, for amorphous regions, especially for APIs or excipients, and hard surfaces. So that can be calcium carbonate fillers with different coatings, or here we have an example of storage stability of an API, which can be very sensitive being measured. That was just an outlook. We want to have more webinars on the results. So, but this result was about sample preparation. And now, what are your learnings? We touched briefly about certain questions which occur when maybe IGC is really a good solution. Yes, you want to have meaningful and reliable results. You hopefully understand the principles, the physical principle of IGC. And with the samples, I've shown that there are a great variety of different samples possible. You should take care of very good reproducible sample preparation. There's a lot which can be done, and that adds to the tips and tricks. We gave you some indication how you find your good experimental conditions, your sweet spot, and finally an outlook of the results and the interpretation, and this is something for later on. I hope you enjoyed it so far. Many thanks. You can contact us anytime for any of your challenges.